The force of the gun must be absorbed by the bucking bar and not the structure being riveted. When the gun is triggered, the rivet is driven. Always make sure the correct rivet header and the retaining spring are installed. Test the rivet gun on a piece of wood and adjust the air valve to a setting that is comfortable for the operator. The driving force of the rivet gun is adjusted by a needle valve on the handle. Adjustments should never be tested against anything harder than a wooden block to avoid header damage. If the adjustment fails to provide the best driving force, a different sized gun is needed. A gun that is too powerful is hard to control and may damage the work. On the other hand, if the gun is too light, it may work to harden the rivet before the head can be fully formed. The riveting action should start slowly and be one continued burst. If the riveting starts too fast, the rivet header might slip off the rivet and damage the rivet, smiley, or damage the skin, eyebrow. Try to drive the rivets within 3 seconds, because the rivet will work harden if the driving process takes too long. The dynamic of the driving process has the gun hitting, or vibrating, the rivet in material, which causes the bar to bounce, or counter-vibrate. These opposing blows, low-frequency vibrations, squeeze the rivet, causing it to swell and then form the upset head. Some precautions to be observed when using a rivet gun are: 1. Never point a rivet gun at anyone at any time. A rivet gun should be used for one purpose only, to drive or install rivets. 2. Never depress the trigger mechanism unless the set is held tightly against a block of wood or a rivet. 3. Always disconnect the air hose from the rivet gun when it is not in use for any appreciable length of time. While traditional tooling has changed little in the past 60 years, significant changes have been made in rivet gun ergonomics. Reduced vibration rivet guns and bucking bars have been developed to reduce the incidence of carpal tunnel syndrome and enhance operator comfort. Rivet sets/headers. Pneumatic guns are used in conjunction with interchangeable rivet sets or headers. Each is designed to fit the type of rivet and location of the work. The shank of the rivet header is designed to fit into the rivet gun. An appropriate header must be a correct match for the rivet being driven. The working face of a header should be properly designed and smoothly polished. They are made of forged steel, heat-treated to be tough but not too brittle. Flush headers come in various sizes. Smaller ones concentrate the driving force in a small area for maximum efficiency. Larger ones spread the driving force over a larger area and are used for the riveting of thin skins. Non-flush headers should fit to contact about the center 2/3 of the rivet head. They must be shallow enough to allow slight upsetting of the head in driving and some misalignment without eyebrowing the riveted surface. Care must be taken to match the size of the rivet. A header that is too small marks the rivet, while one too large marks the material. Rivet headers are made in a variety of styles. Figure 488. The short, straight header is best when the gun can be brought close to the work. Offset headers may be used to reach rivets in obstructed places. Long headers are sometimes necessary when the gun cannot be brought close to the work due to structural interference. Rivet headers should be kept clean. Compression riveting. Compression riveting, squeezing, is of limited value because this method of riveting can be used only over the edges of sheets or assemblies where conditions permit, and where the reach of the rivet squeezer is deep enough. The 3 types of rivet squeezers, hand, pneumatic, and hydraulic, operate on the same principles. In the hand rivet squeezer, compression is supplied by hand pressure, in the pneumatic rivet squeezer, by air pressure, and in the hydraulic, by a combination of air and hydraulic pressure. One jaw is stationary and serves as a bucking bar, the other jaw is movable and does the upsetting. Riveting with a squeezer is a quick method and requires only one operator. These riveters are equipped with either a C-yoke or an alligator yoke in various sizes to accommodate any size of rivet. The working capacity of a yoke is measured by its gap and its reach. The gap is the distance between the movable jaw and the stationary jaw. The reach is the inside length of the throat measured from the center of the end sets. End of page 4-38. End sets for rivet squeezers serve the same purpose as rivet sets for pneumatic rivet guns and are available with the same type heads, which are interchangeable to suit any type of rivet head. One part of each set is inserted in the stationary jaw, while the other part is placed in the movable jaws. The manufactured head end set is placed on the stationary jaw whenever possible. During some operations, it may be necessary to reverse the insets, placing the manufactured head end set on the movable jaw. Microshavers. A microshaver is used if the smoothness of the material, such as skin, requires that all countersunk rivets be driven within a specific tolerance. Figure 489. This tool has a cutter, a stop, and two legs or stabilizers. The cutting portion of the microshaver is inside the stop. The depth of the cut can be adjusted by pulling outward on the stop and turning it in either direction, clockwise for deeper cuts. The marks on the stop permit adjustments of 0.001 inch. If the microshaver is adjusted and held correctly, it can cut the head of a countersunk rivet to within 0.002 inch without damaging the surrounding material. Adjustments should always be made first on scrap material. When correctly adjusted, the microshaver leaves a small round dot about the size of a pinhead on the microshaved rivet. It may occasionally be necessary to shave rivets, normally restricted to MS20426 head rivets, after driving to obtain the required flushness. Shear head rivets should never be shaved. Riveting procedure. The riveting procedure consists of transferring and preparing the hole, drilling, and driving the rivets. Hole transfer. Accomplish transfer of holes from a drilled part to another part by placing the second part over first and using established holes as a guide. Using an alternate method, scribe hole location through from drilled part onto part to be drilled, spot with a center punch, and drill. Hole preparation. It is very important that the rivet hole be of the correct size and shape and free from burrs. If the hole is too small, the protective coating is scratched from the rivet when the rivet is driven through the hole. If the hole is too large, the rivet does not fill the hole completely. When it is bucked, the joint does not develop its full strength, and structural failure may occur at that spot. If countersinking is required, consider the thickness of the metal and adopt the countersinking method recommended for that thickness. If dimpling is required, keep hammer blows or dimpling pressures to a minimum so that no undue work hardening occurs in the surrounding area. Drilling. Rivet holes in repair may be drilled with either a light power drill or a hand drill. The standard shank twist drill is most commonly used. Drill bit sizes for rivet holes should be the smallest size that permits easy insertion of the rivet, approximately 0.003 inch greater than the largest tolerance of the shank diameter. The recommended clearance drill bits for the common rivet diameters are shown in Figure 490. Hole sizes for other fasteners are normally found on work documents, prints, or in manuals. Before drilling, center punch all rivet locations. The center punch mark should be large enough to prevent the drill from slipping out of position, yet it must not dent the surface surrounding the center punch mark. Place a bucking bar behind the metal during punching to help prevent denting. To make a rivet hole the correct size, first drill a slightly undersized hole, pilot hole. Ream the pilot hole with a twist drill of the appropriate size to obtain the required dimension. To drill, proceed as follows. 1. Ensure the drill bit is the correct size and shape. End of page 4 to 39. 2. Place the drill in the center punched mark. When using a power drill, rotate the bit a few turns before starting the motor. 3. While drilling, always hold the drill at a 90 degrees angle to the work or the curvature of the material. For avoid excessive pressure, let the drill bit do the cutting, and never push the drill bit through stock. 5. Remove all burrs with a metal countersink or a file. 6. Clean away all drill chips. When holes are drilled through sheet metal, small burrs are formed around the edge of the hole. This is especially true when using a hand drill because the drill speed is slow and there is a tendency to apply more pressure per drill revolution. Remove all burrs with a burr remover or larger size drill bit before riveting. Driving the rivet. Although riveting equipment can be either stationary or portable, portable riveting equipment is the most common type of riveting equipment used to drive solid shank rivets in airframe repair work. Before driving any rivets into the sheet metal parts, be sure all holes line up perfectly, all shavings and burrs have been removed, and the parts to be riveted are securely fastened with temporary fasteners. Depending on the job, the riveting process may require 1 or 2 people. In solo riveting, the riveter holds a bucking bar with one hand and operates a riveting gun with the other. If the job requires 2 aircraft technicians, a shooter or gunner, and a bucker work together as a team to install rivets. An important component of team riveting is an efficient signaling system that communicates the status of the riveting process. This signaling system usually consists of tapping the bucking bar against the work and is often called the tap code. 1 tap may mean not fully seated, hit it again, while 2 taps may mean good rivet, and 3 taps may mean bad rivet, remove and drive another. Radio sets are also available for communication between the technicians. Once the rivet is installed, there should be no evidence of rotation of rivets or looseness of riveted parts. After the trimming operation, examine for tightness. Apply a force of 10 pounds to the trimmed stem. A tight stem is one indication of an acceptable rivet installation. Any degree of looseness indicates an oversized hole and requires replacement of the rivet with an oversized shank diameter rivet. A rivet installation is assumed satisfactory when the rivet head is seated snugly against the item to be retained. 0.005-inch feeler gauge should not go under rivet head for more than 1/2 the circumference, and the stem is proved tight. Countersunk rivets. An improperly made countersink reduces the strength of a flush riveted joint and may even cause failure of the sheet or the rivet head. The 2 methods of countersinking commonly used for flush riveting in aircraft construction and repair are: 1. Machine or drill countersinking. 2. Dimpling or press countersinking. The proper method for any particular application depends on the thickness of the parts to be riveted, the height and angle of the countersunk head, the tools available, and accessibility. Countersinking. When using countersunk rivets, it is necessary to make a conical recess in the skin for the head. The type of countersink required depends upon the relation of the thickness of the sheets to the depth of the rivet head. Use the proper degree and diameter countersink and cut only deep enough for the rivet head and metal to form a flush surface. Countersinking is an important factor in the design of fastener patterns, as the removal of material in the countersinking process necessitates an increase in the number of fasteners to assure the required load transfer strength. If countersinking is done on metal below a certain thickness, a knife edge with less than the minimum bearing surface or actual enlarging of the hole may result. The edge distance required when using countersunk fasteners is greater than when universal head fasteners are used. The general rule for countersinking and flush fastener installation procedures has been re-evaluated in recent years because countersunk holes have been responsible for fatigue cracks in aircraft pressurized skin. In the past, the general rule for countersinking held that the fastener head must be contained within the outer sheet. A combination of countersinks too deep, creating a knife edge, number of pressurization cycles, fatigue, deterioration of bonding materials, and working fasteners caused a high stress concentration that resulted in skin cracks and fastener failures. In primary structure and pressurized skin repairs, some manufacturers are currently recommending the countersink depth be no more than 2/3 the outer sheet thickness or down to 0.020-inch minimum fastener shank depth, whichever is greater. Dimple the skin if it is too thin for machine countersinking. Figure 4.91. Keep the rivet high before driving to ensure the force of riveting is applied to the rivet and not to the skin. If the rivet is driven while it is flush or too deep, the surrounding skin is work hardened. End of page 4-40. Countersinking tools. While there are many types of countersink tools, the most commonly used has an included angle of 100 degrees. Sometimes types of 82 degrees or 120 degrees are used to form countersunk wells. Figure 4.84. A 6-fluted countersink works best in aluminum. There are also 4 and 3-fluted countersinks, but those are harder to control from a chatter standpoint. A single flute type, such as those manufactured by the Weldon Tool Company, works best for corrosion-resistant steel. Figure 4.92. The microstop countersink is the preferred countersinking tool. Figure 4.85. It has an adjustable sleeve cage that functions as a limit stop and holds the revolving countersink in a vertical position. Its threaded and replaceable cutters may have either a removable or an integral pilot that keeps the cutter centered in the hole. The pilot should be approximately 0.002 inch smaller than the hole size. It is recommended to test adjustments on a piece of scrap material before countersinking repair or replacement parts. Freehand countersinking is needed where a microstop countersink cannot fit. This method should be practiced on scrap material to develop the required skill. Holding the drill motor steady and perpendicular is as critical during this operation as when drilling. Chattering is the most common problem encountered when countersinking. Some precautions that may eliminate or minimize chatter include: 1. Use sharp tooling. 2. Use a slow speed and steady firm pressure. 3. Use a piloted countersink with a pilot approximately 0.002 inch smaller than the hole. 4. Use backup material to hold the pilot steady when countersinking thin sheet material. 5. Use a cutter with a different number of flutes. 6. Pilot drill an undersized hole, countersink, and then enlarge the hole to final size. Dimpling. Dimpling is the process of making an indentation or a dimple around a rivet hole to make the top of the head of a countersunk rivet flush with the surface of the metal. Dimpling is done with a male and female die, or forms, often called punch and die set. The male die has a guide the size of the rivet hole and is beveled to correspond to the degree of countersink of the rivet head. The female die has a hole into which the male guide fits and is beveled to a corresponding degree of countersink. When dimpling, rest the female die on a solid surface. Then, place the material to be dimpled on the female die. Insert the male die in the hole to be dimpled and, with a hammer, strike the male die until the dimple is formed. 2 or 3 solid hammer blows should be sufficient. A separate set of dies is necessary for each size of rivet and shape of rivet head. An alternate method is to use a countersunk head rivet instead of the regular male punch die, and a draw set instead of the female die, and hammer the rivet until the dimple is formed. Dimpling dies for light work can be used in portable pneumatic or hand squeezers. Figure 4.93. If the dies are used with a squeezer, they must be adjusted accurately to the thickness of the sheet being dimpled. A table riveter is also used for dimpling thin skin material and installing rivets. Figure 4.94. End of page 4 to 41. Coin dimpling. The coin dimpling, or coin pressing, method uses a countersink rivet as the male dimpling die. Place the female die in the usual position and back it with a bucking bar. Place the rivet of the required type into the hole and strike the rivet with a pneumatic riveting hammer. Coin dimpling should be used only when the regular male die is broken or not available. Coin pressing has the distinct disadvantage of the rivet hole needing to be drilled to correct rivet size before the dimpling operation is accomplished. Since the metal stretches during the dimpling operation, the hole becomes enlarged and the rivet must be swelled slightly before driving to produce a close fit. Because the rivet head causes slight distortions in the recess, and these are characteristic only to that particular rivet head, it is wise to drive the same rivet that was used as the male die during the dimpling process. Do not substitute another rivet, either of the same size or a size larger. Radius dimpling. Radius dimpling uses special die sets that have a radius and are often used with stationary or portable squeezers. Dimpling removes no metal and, due to the nestling effect, gives a stronger joint than the non-flush type. A dimpled joint reduces the shear loading on the rivet and places more load on the riveted sheets. Note, dimpling is also done for flush bolts and other flush fasteners. Dimpling is required for sheets that are thinner than the minimum specified thickness for countersinking. However, dimpling is not limited to thin materials. Heavier parts may be dimpled without cracking by specialized hot dimpling equipment. The temper of the material, rivet size, and available equipment are all factors to be considered in dimpling. Figure 4.95. Hot dimpling. Hot dimpling is the process that uses heated dimpling dies to ensure the metal flows better during the dimpling process. End of page 4 to 42. Hot dimpling is often performed with large stationary equipment available in a sheet metal shop. The metal being used is an important factor because each metal presents different dimpling problems. For example, 2024 T3 aluminum alloy can be satisfactorily dimpled either hot or cold, but may crack in the vicinity of the dimple after cold dimpling because of hard spots in the metal. Hot dimpling prevents such cracking. 7075T6 aluminum alloys are always hot dimpled. Magnesium alloys also must be hot dimpled because, like 7075T6, they have low formability qualities. Titanium is another metal that must be hot dimpled because it is tough and resists forming. The same temperature and dwell time used to hot dimple 7075T6 is used for titanium. 100 degrees combination pre-dimple and countersink method metals of different thicknesses are sometimes joined by a combination of dimpling and countersinking. Figure 4.96. A countersink well made to receive a dimple is called a subcountersink. These are most often seen where a thin web is attached to heavy structure. It is also used on thin gap seals, or strips, and repairs for worn countersinks. Dimpling inspection. To determine the quality of a dimple, it is necessary to make a close visual inspection. Several features must be checked. The rivet head should fit flush and there should be a sharp break from the surface into the dimple. The sharpness of the break is affected by dimpling pressure and metal thickness. Selected dimples should be checked by inserting a fastener to make sure that the flushness requirements are met. Cracked dimples are caused by poor dies, rough holes, or improper heating. Two types of cracks may form during dimpling. 1. Radial cracks start at the edge and spread outward as the metal within the dimple stretches. They are most common in 2024 T3. A rough hole or a dimple that is too deep causes such cracks. A small tolerance is usually allowed for radial cracks. 2. Circumferential cracks downward bending into the draw die causes tension stresses in the upper portion of the metal. Under some conditions, a crack may be created that runs around the edge of the dimple. Such cracks do not always show since they may be underneath the cladding. When found, they are cause for rejection. These cracks are most common in hot dimpled 7075T6 aluminum alloy material. The usual cause is insufficient dimpling heat. Evaluating the rivet. To obtain high structural efficiency in the manufacture and repair of aircraft, an inspection must be made of all rivets before the part is put in service. This inspection consists of examining both the shop and manufactured heads and the surrounding skin and structural parts for deformities. A scale or rivet gauge can be used to check the condition of the upset rivet head to see that it conforms to the proper requirements. Deformities in the manufactured head can be detected by the trained eye alone. Figure 4.97. Some common causes of unsatisfactory riveting are improper bucking, rivet sets slipping off or being held at the wrong angle, and rivet holes or rivets of the wrong size. Additional causes for unsatisfactory riveting are countersunk rivets not flush with the well, work not properly fastened together during riveting, the presence of burrs, rivets too hard, too much or too little driving, and rivets out of line. Occasionally, during an aircraft structural repair, it is wise to examine adjacent parts to determine the true condition of neighboring rivets. In doing so, it may be necessary to remove the paint. The presence of chipped or cracked paint around the heads may indicate shifted or loose rivets. Look for tipped or loose rivet heads. If the heads are tipped or if rivets are loose, they show up in groups of several consecutive rivets and probably tipped in the same direction. If heads that appear to be tipped are not in groups and are not tipped in the same direction, tipping may have occurred during some previous installation. Inspect rivets known to have been critically loaded, but that show no visible distortion, by drilling off the head and carefully punching out the shank. If, upon examination, the shank appears joggled and the holes in the sheet misaligned, the rivet has failed in shear. In that case, try to determine what is causing the shearing stress and take the necessary corrective action. Flush rivets that show head slippage within the countersink or dimple, indicating either sheet bearing failure or rivet shear failure, must be removed for inspection and replacement. Joggles in removed rivet shanks indicate partial shear failure. Replace these rivets with the next larger size. Also, if the rivet holes show elongation, replace the rivets with the next larger size. End of page 4 to 43. Sheet failures such as tear-outs, cracks between rivets, and the like usually indicate damaged rivets. The complete repair of the joint may require replacement of the rivets with the next larger size. The general practice of replacing a rivet with the next larger size, 1/32 inch greater diameter, is necessary to obtain the proper joint strength of rivet and sheet when the original rivet hole is enlarged. If the rivet in an elongated hole is replaced by a rivet of the same size, its ability to carry its share of the shear load is impaired and joint weakness results. Removal of rivets. When a rivet has to be replaced, remove it carefully to retain the rivet hole's original size and shape. If removed correctly, the rivet does not need to be replaced with one of the next larger size. Also, if the rivet is not removed properly, the strength of the joint may be weakened and the replacement of rivets made more difficult. When removing a rivet, work on the manufactured head. It is more symmetrical about the shank than the shop head, and there is less chance of damaging the rivet hole or the material around it. To remove rivets, use hand tools, a power drill, or a combination of both. The procedure for universal or protruding head rivet removal is as follows. 1. File a flat area on the head of the rivet and center punch the flat surface for drilling. Note, on thin metal, back up the rivet on the upset head when center punching to avoid depressing the metal. 2. Use a drill bit one size smaller than the rivet shank to drill out the rivet head. Note, when using a power drill, set the drill on the rivet and rotate the chuck several revolutions by hand before turning on the power. This procedure helps the drill cut a good starting spot and eliminates the chance of the drill slipping off and tracking across the metal. 3. Drill the rivet to the depth of its head, while holding the drill at a 90 degrees angle. Do not drill too deeply, as the rivet shank will then turn with the drill and tear the surrounding metal. Note, the rivet head often breaks away and climbs the drill, which is a signal to withdraw the drill. End of page 4 to 44. 4. If the rivet head does not come loose of its own accord, insert a drift punch into the hole and twist slightly to either side until the head comes off. 5. Drive the remaining rivet shank out with a drift punch slightly smaller than the shank diameter. On thin metal or unsupported structures, support the sheet with a bucking bar while driving out the shank. If the shank is unusually tight after the rivet head is removed, drill the rivet about 2/3 through the thickness of the material and then drive the rest of it out with a drift punch. Figure 4.98 shows the preferred procedure for removing universal rivets. The procedure for the removal of countersunk rivets is the same as described above, except no filing is necessary. Be careful to avoid elongation of the dimpled or the countersunk holes. The rivet head should be drilled to approximately 1/2 the thickness of the top sheet. The dimple in 2117T rivets usually eliminates the necessity of filing and center punching the rivet head. To remove a countersunk or flush head rivet, you must 1. Select a drill about 0.003 inch smaller than the rivet shank diameter. 2. Drill into the exact center of the rivet head to the approximate depth of the head. 3. Remove the head by breaking it off. Use a punch as a lever. 4. Punch out the shank. Use a suitable backup, preferably wood, or equivalent, or a dedicated backup block. If the shank does not come out easily, use a small drill and drill through the shank. Be careful not to elongate the hole. Replacing rivets. Replace rivets with those of the same size and strength whenever possible. If the rivet hole becomes enlarged, deformed, or otherwise damaged, drill or ream the hole for the next larger size rivet. Do not replace a rivet with a type having lower strength properties, unless the lower strength is adequately compensated by an increase in size or a greater number of rivets. It is acceptable to replace 2017 rivets of 3/16 inch diameter or less, and 2024 rivets of 5/32 inch diameter or less with 2117 rivets for general repairs, provided the replacement rivets are 1/32 inch greater in diameter than the rivets they replace. National Advisory Committee for Aeronautics, NACA, method of double flush riveting. A rivet installation technique known as the National Advisory Committee for Aeronautics, NACA, method has primary applications in fuel tank areas. Figure 4.99. To make a NACA rivet installation, the shank is upset into a 82 degrees countersink. In driving, the gun may be used on either the head or shank side. The upsetting is started with light blows, then the force increased and the gun or bar moved on the shank end so as to form a head inside the countersink well. If desired, the upset head may be shaved flush after driving. If utilizing this method, it is important to reference the manufacturer's instructions for repair or replacement. Special Purpose Fasteners. Special purpose fasteners are designed for applications in which fastener strength, ease of installation, or temperature properties of the fastener require consideration. Solid shank rivets have been the preferred construction method for metal aircraft for many years because they fill up the hole, which results in good load transfer, but they are not always ideal. For example, the attachment of many non-structural parts, aircraft interior furnishings, flooring, de-icing boots, etc., do not need the full strength of solid shank rivets. To install solid shank rivets, the aircraft technician must have access to both sides of a riveted structure or structural part. There are many places on an aircraft where this access is impossible or where limited space does not permit the use of a bucking bar. In these instances, it is not possible to use solid shank rivets, and special fasteners have been designed that can be bucked from the front. Figure 4, 100. There are also areas of high loads, high fatigue, and bending on aircraft. Although the shear loads of riveted joints are very good, the tension, or clamp-up, loads are less than ideal. Special purpose fasteners are sometimes lighter than solid shank rivets, yet strong enough for their intended use. These fasteners are manufactured by several corporations and have unique characteristics that require special installation tools, special installation procedures, and special removal procedures. Because these fasteners are often inserted in locations where one head, usually the shop head, cannot be seen, they are called blind rivets or blind fasteners. Typically, the locking characteristics of a blind rivet are not as good as a driven rivet. Therefore, blind rivets are usually not used when driven rivets can be installed. Blind rivets shall not be used. 1. In fluid-tight areas. 2. On aircraft in air intake areas where rivet parts may be ingested by the engine. 3. On aircraft control surfaces, hinges, hinge brackets, flight control actuating systems, wing attachment fittings, landing gear fittings, on floats or amphibian hulls below the water level, or other heavily stressed locations on the aircraft. End of page 4 to 45. Figure 4, 98. Rivet removal. Figure 4, 99. NACA riveting method. Figure 4, 100. Assorted fasteners. End of page 4 to 46. Note, for metal repairs to the airframe, the use of blind rivets must be specifically authorized by the airframe manufacturer or approved by a representative of the Federal Aviation Administration, FAA. Blind rivets. The first blind fasteners were introduced in 1940 by the Cherry Rivet Company, now Cherry Aerospace, and the aviation industry quickly adopted them. The past decades have seen a proliferation of blind fastening systems based on the original concept, which consists of a tubular rivet with a fixed head and a hollow sleeve. Inserted within the rivet's core is a stem that is enlarged or serrated on its exposed end when activated by a pulling-type rivet gun. The lower end of the stem extends beyond the inner sheet of metal. This portion contains a tapered joining portion and a blind head that has a larger diameter than the stem or the sleeve of the tubular rivet. When the pulling force of the rivet gun forces the blind head upward into the sleeve, its stem upsets or expands the lower end of the sleeve into a tail. This presses the inner sheet upward and closes any space that might have existed between it and the outer sheet. Since the exposed head of the rivet is held tightly against the outer sheet by the rivet gun, the sheets of metal are clamped, or clinched, together. Note, fastener manufacturers use different terminology to describe the parts of the blind rivet. The terms mandrel, spindle, and stem are often used interchangeably. For clarity, the word stem is used in this handbook and refers to the piece that is inserted into the hollow sleeve. Friction-locked blind rivets. Standard self-plugging blind rivets consist of a hollow sleeve and a stem with increased diameter in the plug section. The blind head is formed as the stem is pulled into the sleeve. Friction-locked blind rivets have a multiple-piece construction and rely on friction to lock the stem to the sleeve. As the stem is drawn up into the rivet shank, the stem portion upsets the shank on the blind side, forming a plug in the hollow center of the rivet. The excess portion of the stem breaks off at a groove due to the continued pulling action of the rivet gun. Metals used for these rivets are 2117T4 and 5056F aluminum alloy. Monel is used for special applications. Many friction-locked blind rivet center stems fall out due to vibration, which greatly reduces its shear strength. To combat that problem, most friction-lock blind rivets are replaced by the mechanical lock or stem lock type of blind fasteners. However, some types, such as the Cherry SPR 3/32" self-plugging rivet, are ideal for securing nut plates located in inaccessible and hard-to-reach areas where bucking or squeezing of solid rivets is unacceptable. Figure 4.101. Friction-lock blind rivets are less expensive than mechanical lock blind rivets and are sometimes used for non-structural applications. Inspection of friction-lock blind rivets is visual. A more detailed discussion on how to inspect riveted joints can be found later in this chapter. Removal of friction-lock blind rivets consists of punching out the friction-lock stem and then treating it like any other rivet. Mechanical lock blind rivets. The self-plugging, mechanical lock blind rivet was developed to prevent the problem of losing the center stem due to vibration. This rivet has a device on the puller or rivet head that locks the center stem into place when installed. Bulb, self-plugging, mechanically locked blind rivets form a large blind head that provides higher strength in thin sheets when installed. They may be used in applications where the blind head is formed against a dimpled sheet. Manufacturers such as Cherry Aerospace, Cherry Max, Cherry Lock, Cherry SST, and Alcoa Fastening Systems, Huck Clinch, Huck Max, Automatic, make many variations of this blind rivet. While similar in design, the tooling for these rivets is often not interchangeable. The Cherry Max bulbed blind rivet is one of the earlier types of mechanical lock blind rivets developed. End of page 4-47. Their main advantage is the ability to replace a solid shank rivet size for size. The Cherry Max bulbed blind rivet consists of 4 parts. 1. A fully serrated stem with brake notch, shear ring, and integral grip adjustment cone. 2. A driving anvil to ensure a visible mechanical lock with each fastener installation. 3. A separate, visible, and inspectable locking collar that mechanically locks the stem to the rivet sleeve. 4. A rivet sleeve with recess in the head to receive the locking collar. It is called a bulbed fastener due to its large blind side bearing surface, developed during the installation process. These rivets are used in thin sheet applications and for use in materials that may be damaged by other types of blind rivets. This rivet features a SafeLock locking collar for more reliable joint integrity. The rough end of the retained stem in the center on the manufactured head must never be filed smooth because it weakens the strength of the lock ring, and the center stem could fall out. Cherry Max bulbed rivets are available in 3 head styles: universal, 100 degrees countersunk, and 100 degrees reduced shear head styles. Their lengths are measured in increments of 1/16 inch. It is important to select a rivet with a length related to the grip length of the metal being joined. This blind rivet can be installed using either the Cherry G750A or the newly released Cherry G800 hand riveters, or either the pneumatic hydraulic G704B or G747 Cherry Max power tools. For installation, please refer to Figure 4.102. The Cherry Max mechanical lock blind rivet is popular with general aviation repair shops because it features the one tool concept to install 3 standard rivet diameters and their oversized counterparts. Figure 4.103. Cherry Max rivets are available in 4 nominal diameters: 1/8, 5/32, 3/16, and 1/4 inch, and 3 oversized diameters in 4 head styles: universal, 100 degrees flush head, 120 degrees flush head, and an S1097 flush head. This rivet consists of a blind header, hollow rivet shell, locking, foil, collar, driving anvil, and pulling stem complete with wrapped locking collar. The rivet sleeve and the driving washer blind bulbed header takes up the extended shank and forms the bucktail. The stem and rivet sleeve work as an assembly to provide radial expansion and a large bearing footprint on the blind side of the fastened surface. The lock collar ensures that the stem and sleeve remain assembled during joint loading and unloading. Rivet sleeves are made from 5056 aluminum, Monel, and INCO 600. The stems are made from alloy steel, Cress, and INCO X750. Cherry Max rivets have an ultimate shear strength ranging from 50 ksi to 75 ksi. Removal of mechanically locked blind rivets. Mechanically locked blind rivets are a challenge to remove because they are made from strong, hard metals. End of page 4 to 48. Lack of access poses yet another problem for the aviation technician. Designed for and used in difficult to reach locations means there is often no access to the blind side of the rivet or any way to provide support for the sheet metal surrounding the rivet's location when the aviation technician attempts removal. The stem is mechanically locked by a small lock ring that needs to be removed first. Use a small center drill to provide a guide for a larger drill on top of the rivet stem and drill away the upper portion of the stem to destroy the lock. Try to remove the lock ring or use a prick punch or center punch to drive the stem down a little and remove the lock ring. After the lock ring is removed, the stem can be driven out with a drive punch. After the stem is removed, the rivet can be drilled out in the same way as a solid rivet. If possible, support the backside of the rivet with a backup block to prevent damage to the aircraft skin. Pin fastening systems, high-shear fasteners. A pin fastening system, or high-shear pin rivet, is a two-piece fastener that consists of a threaded pin and a collar. The metal collar is swaged onto the grooved end, affecting a firm tight fit. They are essentially threadless bolts. High-shear rivets are installed with standard bucking bars and pneumatic riveting hammers. They require the use of a special gun set that incorporates collar swaging and trimming and a discharge port through which excess collar material is discharged. A separate size set is required for each shank diameter. Installation of high-shear fasteners. Prepare holes for pin rivets with the same care as for other close tolerance rivets or bolts. At times, it may be necessary to spot face the area under the head of the pin to ensure the head of the rivet fits tightly against the material. The spot-faced area should be 1/16 inch larger in diameter than the head diameter. Pin rivets may be driven from either end. Procedures for driving a pin rivet from the collar end are: 1. Insert the rivet in the hole. 2. Place a bucking bar against the rivet head. 3. Slip the collar over the protruding rivet end. 4. Place previously selected rivet set and gun over the collar. Align the gun until it is perpendicular to the material. 5. Depress the trigger on the gun, applying pressure to the rivet collar. This action causes the rivet collar to swage into the groove on the rivet end. 6. Continue the driving action until the collar is properly formed and excess collar material is trimmed off. Procedures for driving a pin rivet from the head end are: 1. Insert the rivet in the hole. 2. Slip the collar over the protruding end of rivet. 3. Insert the correct size gun rivet set in a bucking bar and place the set against the collar of the rivet. 4. Apply pressure against the rivet head with a flush rivet set and pneumatic riveting hammer. End of page 4 to 49. 5. Continue applying pressure until the collar is formed and the groove and excess collar material is trimmed off. Inspection. Pin rivets should be inspected on both sides of the material. The head of the rivet should not be marred and should fit tightly against the material. Removal of pin rivets. The conventional method of removing rivets by drilling off the head may be utilized on either end of the pin rivet. Center punching is recommended prior to applying drilling pressure. In some cases, alternate methods may be needed. 1. Grind a chisel edge on a small pin punch to a blade width of 1/8 inch. Place this tool at right angles to the collar and drive with a hammer to split the collar down one side. Repeat the operation on the opposite side. Then, with the chisel blade, pry the collar from the rivet. Tap the rivet out of the hole. 2. Use a special hollow punch having one or more blades placed to split the collar. Pry the collar from the groove and tap out the rivet. 3. Sharpen the cutting blades of a pair of nippers. Cut the collar in 2 pieces or use nippers at right angles to the rivet and cut through the small neck. 4. A hollow mill collar cutter can be used in a power hand drill to cut away enough collar material to permit the rivet to be tapped out of the work. The High-Shear pin rivet family includes fasteners such as the High-Lock, High-Teague, and High-Light made by High-Shear Corporation and the Cherry Buck 95 KSI one-piece shear pin and Cherry Easy Buck shear pin made by Cherry Aerospace. High-Lock Fastening System. The threaded end of the High-Lock two-piece fastener contains a hexagonal-shaped recess. Figure 4.104. The hex tip of an Allen wrench engages the recess to prevent rotation of the pin while the collar is being installed. The pin is designed in two basic head styles. For shear applications, the pin is made in countersunk style and in a compact protruding head style. For tension applications, the MS-24694 countersunk and regular protruding head styles are available. The self-locking, threaded High-Lock collar has an internal counterbore at the base to accommodate variations in material thickness. At the opposite end of the collar is a wrenching device that is torqued by the driving tool until it shears off during installation, leaving the lower portion of the collar seated with the proper torque without additional torque inspection. This shear-off point occurs when a predetermined preload or clamp-up is attained in the fastener during installation. The advantages of High-Lock two-piece fastener include its lightweight, high fatigue resistance, high strength, and its inability to be over-torqued. The pins, made from alloy steel, corrosion-resistant steel, or titanium alloy, come in many standard and oversized shank diameters. The collars are made of aluminum alloy, corrosion-resistant steel, or alloy steel. The collars have wrenching flats, fractured point, threads, and a recess. The wrenching flats are used to install the collar. The fracture point has been designed to allow the wrenching flats to shear when the proper torque has been reached. The threads match the threads of the pins and have been formed into an ellipse that is distorted to provide the locking action. The recess serves as a built-in washer. This area contains a portion of the shank and the transition area of the fastener. The hole shall be prepared so that the maximum interference fit does not exceed 0.002 inch. This avoids buildup of excessive internal stresses in the work adjacent to the hole. The High-Lock pin has a slight radius under its head to increase fatigue life. After drilling, deburr the edge of the hole to allow the head to seat fully in the hole. The High-Lock is installed in interference fit holes for aluminum structure and a clearance fit for steel, titanium, and composite materials. High-Teague Fastening System. The High-Teague fastener offers all of the benefits of the High-Lock fastening system along with a unique bead design that enhances the fatigue performance of the structure, making it ideal for situations that require a controlled interference fit. The High-Teague fastener assembly consists of a pin and collar. These pin rivets have a radius at the transition area. During installation in an interference fit hole, the radius area will cold work the hole. These fastening systems can be easily confused, and visual reference should not be used for identification. Use part numbers to identify these fasteners. End of page 4 to 50.